Now we have the topic representation of coordination compounds. So in coordination compounds, we can see one square bracket inside which there is a coordination sphere, and outside of this square bracket there is ionization sphere. The portion inside the square bracket is called coordination sphere, and outside of this square bracket it is called ionization sphere. The main important points to be remembered from this coordination sphere is that the number of ligands or number of donor atom attached to this central metal atom represents the coordination number. The coordination number of the metal atom. So in this case, we can see that the nickel has total 6 NH3 group attached to it. So the coordination number in this case is 6, and obviously some other elements, that is 2 chloride ion, is outside this coordination sphere. As we have already discussed about this, that it will represent or it will satisfy the primary valency. So inside this coordination sphere, these groups are called ligands. When we dissolve this coordination compound in water, it will dissociate into nickel NH3 6 2 plus 2Cl minus ion. So it is like after dissolving in water, it will break into two parts. That is, it will break according to the primary valency. And inside of this coordination sphere, all the entities inside this coordination sphere will remain intact. In case of coordination compound, the metal atom is behaving like a Lewis acid, and the ligand group, which is donating a pair of electron, is behaving as Lewis base, eventually forming this metal ligand coordinate bond. So let's check the definition of ligand. We have already discussed about ligand in our earlier discussion. Any species which can donate at least one electron pair to metal or metal cation is called ligand. For example, water, NH3, Cl, etc. So let's check the types of ligand and their classifications according to their donating ability in our next portion. So the next topic is classification of ligand on the basis of number of donor atoms, or we can simply say that on the basis of denticity. So first we have monodentate ligand. So in case of monodentate ligand, they have only one donor atom. Only one donor atom. It is like it can be made up of more than one atom, but the number of ultimate donating atom is only one. That is, for example, fluoride. This ion is a ligand, but it is a monodentate ligand because it can donate electron only via one atom. Similarly, chloride, bromide, etc. Other examples like NH2 minus. The naming is also important. This is called amido. I will mention all the important ligands in my discussion and also mention their naming. Like for F minus, it will be called as fluorido. Cl minus will be called as chlorido. You can see that O is added in the last portion of the name of this ligand. Similarly, it is iodo. bromido, carbonato, PO4 3 minus, phosphato, ClO4 minus, perchlorato, NO3 minus, nitrato, MEO minus, methoxide, S2O3 2 minus, thiosulfato. Here I am showing this dash because this thiocyanate is connecting to the metal ion via sulfur atom, and the name is thiocyanate S. Thiocyanate S. And similarly, it is connecting via nitrogen atom, the same name, but we will put N here. Similarly, in this case, this ligand is connecting via nitrogen atom. That's why nitrogen is here. We are writing nitrogen in this name. On the other hand, here it is connecting via oxygen atom. That's why we are writing oxygen here. These are all important and very useful ligand while naming our coordination compounds. I'm writing all these names section by section. The last portion is not containing O in its end. See, NH3 is called amine and H2O is called aqua. Here no O is present in the end. CO is called carbonyl. So these are all important ligands. We will have some other important ligands in our later discussions. Next, we have a very important point about positively charged ligand. There are some positively charged ligand as well, like NO plus, nitrosonium ligand, hydrazinium, and nitronium. These three are positively charged ligand. One important discussion about NO ligand is that NO ligand can exist as NO plus and NO minus. That is, NO ligand can be present as NO plus and NO minus in coordination as well as in organometallic compounds. The main important points to be noted are, this is simple NO, that is in its neutral state. When we add one electron, it will become NO minus. Similarly, when we remove one electron, it will become NO plus. The main structures are, there are two electrons in each orbital of nitrogen. So when this NO minus connects with metal ion, it will form a band bond with the metal ion. It is very important. The structure is band. So the form of NO is band in case of NO minus. And in case of NO plus, the structure is and when it binds with metal, it forms a linear pattern. That is, it is linear when the NO is plus. It is a very important point to note down. And if the NO is neutral, then the structure is neutral form. So when this neutral NO connects with metal, it will form like this, and this unpaired electron will be donated to the vacant orbital of metal ion. So in this neutral form, NO is donating all total 3 electrons to the metal ion. That is donation of 3 electrons. So in summary, we can conclude that when the NO is neutral, then it will donate 3 electrons, and when these NO is positively or negatively charged, then it will donate 2 electrons to the metal ion. So another important point is that when both paired and unpaired electron is present, then it will always donate the unpaired electron. When NO is present in iron complexes, it will be always as NO plus. Always remember. So for example, the common coordination complex of iron, water. Here the charge of NO is +1, water has 0 charge, and iron has +1 charge. And we all know that this compound is responsible for the brown color in brown ring test for nitrate. It is responsible for brown coloration in brown ring test for nitrate. So let's check the important brown ring test chemical equation. So another important coordination complex that contains iron and NO ligand used in our daily chemistry life, that is sodium nitro sodium nitroprusside. So when this coordination complex gets ionized, then it will be ionized as 2Na plus ion, and this coordination compound. This compound will break according to their primary valency, but not the entity present inside this coordination sphere will dissociate. So here the oxidation numbers are iron. If NO is present with iron, then obviously it will be +1. Then 1 CN contains 1 minus charge. Then total 5, it will have -5, and iron has this 2 plus charge. So overall the charge is 2 minus in from this coordination sphere, and outside of this coordination sphere, to counter this 2 minus charge, there is 2 sodium plus ions are present outside this coordination sphere. So the use of this sodium nitroprusside complex is this complex is of red color, and when it connects with sulfide ion, it will change its color into purple color, forming this complex. Purple color. So the use of this sodium nitroprusside is to test of sulfide ion. So these are some important iron and NO ligand complexes used in various chemical. Another important point is the electronic configuration of iron is, and when we remove one electron in its gaseous state, that is in free state, the electronic configuration will become this will be its electronic configuration in free or gaseous state. That is, it is not in a coordination complex. Iron is free and it is present in gaseous state. But whenever it is present in complex form, the electronic configuration will be, it is happening because of the splitting of d orbital. As we all know that in presence of ligand field, the d orbital of transition metal atom splits into two parts. So the electrons will fill according to the energy state. The orbitals having lower energy state will be filled first, then it will go to the higher energy level orbital. So in case of the complex form, that is when iron plus is present in complex form, that is in coordination complex, the electronic configuration of iron plus will be like this, and it is different from the free gaseous state of iron plus electronic configuration. The reason is due to d orbital splitting.